Section 37 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 1. Edited by Francis Rolt-Wheeler. Astronomy, Chapter 24. Nebulae and Star Clusters, Part 2. After the spectroscope, photography has been found a most valuable method of nebular research, and many discoveries have been recorded through its assistance. It will be appreciated readily that an impression left by visual observation in a matter of this kind would necessarily be very vague, and, furthermore, that the record on a sensitive plate by long exposure would show far more detail than even the eye of the observer can perceive. Accordingly, all the great observatories of the world, particularly those equipped with good reflecting telescopes, have been at work on nebular photographs since about 1880, though it was not until 1883 that the first really excellent pictures were obtained. It was early seen that the light of nebulae was strongly photographic, and that it was really more actinic than visual. A photograph with a long exposure showed the Merope nebulae in the Pleiades just as the best observers had drawn it, and at the same time filled the entire group of stars with an entangling system of nebulous matter which seemed to bind together the different stars of the group with misty wreaths and streams of filmy light, nearly all of which detail is entirely beyond the keenest vision and the most powerful telescope. After Sir William Huggins, with his spectroscope, had endeavored in vain to determine the radial movements of nebulae, Professor James E. Keeler repeated the attempt at Licht Observatory in 1890-91 and achieved great success. 10 planetary nebulae showed satisfactory evidence of line of sight motion, one of which, the well-known greenish globe in Draco, was found to be moving toward the Earth at a rate of 40 miles a second, while the Orion nebula was receding at a rate of 11 miles. Keeler's work demonstrated that no longer should nebular fixity be looked upon as a fact, and that nebulae have a motion which can be studied. Again the sensitive plate had scored a triumph. The study of nebulae has led to their classification under various heads into spiral, planetary, ring and irregular nebulae. The first spiral nebulae was discovered by Lord Rosse (1800 to 1867) with his great 6-foot reflecting telescope, which was mounted at Parsonstown, Ireland. A typical spiral nebula consists of a central disc-shaped portion or nucleus, with 2 long curved arms projecting from opposite sides, giving the effect of rapid rotary movement and slightly suggesting the familiar pinwheel of firework displays. The chief characteristic of the spiral nebula is their white color as compared with the greenish tinge of other types. Furthermore, they are more numerous than all other types combined, it having been estimated by the late Professor Keeler of Lick Observatory that at least 120,000 of these spirals were within the grasp of the Crossley reflector of that institution, while Professor Perrine at the same observatory increases the estimate to 500,000 and believes that with a more sensitive photographic plate and a long exposure over 1,000,000 could be obtained. According to their spectra they are largely in a solid or liquid condition, but are of a tenuous character and very transparent, so that it is inferred that they consist of vast swarms of incandescent solid or liquid material surrounded by gaseous material. The nebula in Andromeda is the greatest spiral known. Its diameter is more than 500,000 times the distance from the Earth to the Sun, or 8 light years. It is visible to the naked eye and is second only to that of Orion in size and splendor. It has frequently been mistaken for a comet. If it were 1/20,000,000th as condensed as the Sun, it would attract the Earth as much as the Sun does. The extreme rarity or tenuity of nebulae is evident from the fact that there is no evidence that we have the slightest disturbance of the motions of even those stars nearest to them. Planetary nebulae consist of small, round, elliptical disks of light, appearing much like the planets. Hence their name. In the spectra of these nebulae are found bright lines in the green portion, which are characteristic of no terrestrial substance. Accordingly, a hypothetical gas, nebulum, was assumed by Sir William Huggins (1868) to correspond with these lines. At first Lockyer in England believed that the green line in nebulum was due to magnesium oxide, but this was entirely disproved by Keeler. The nuclei of planetary nebulae are often bright as if to indicate that condensation is taking place at their centers. The smaller and even brighter nebulae are possibly representative of a final stage of planetary nebulae, or else they become stars and are then known as stellar nebulae. A few ring nebulae are found which have an annular shape, the center of the ring being filled with nebulous light. Hence it may be assumed that the ring nebulae are brighter around the circumference than at the center. The most striking and typical ring nebula is that of Lyra. The Orion nebula, which, as we have said, is the largest of nebulae, is typical of irregular nebulae and is also one of the most beautiful bodies in the heavens. It is situated in the center of the sword of Orion, and from the time of Sir William Huggins has been studied extensively with the spectroscope. The bright lines of nebulum and hydrogen are noted in the spectrum, which shows conclusively that it is a mass of glowing gas. This nebula represents a vast amount of material, and if the theory that the condensation of such material produces stars needs proof, here obviously are the sources of many suns in a very rough stage of development. The distribution of nebulae, as Herschel noted, is quite the reverse of that of the stars. They are less numerous in the Milky Way, increasing in number as we go from it in any direction. A speculative explanation advanced is that the two regions of maximum nebulae represent places where they have not yet condensed into stars. Not only the spectroscopic evidence of bright lines, but the aspect of nebulae themselves shows that they are transparent through and through. This is remarkable when taken in connection with their inconceivable size. Leaving out the large diffused nebulae which we have mentioned, these objects are frequently several minutes in diameter. Of their distance we know nothing except that they are probably situated in the distant stellar regions. Their parallax can be but a small fraction of a second. We shall probably err greatly in excess if we assume that it varies between 100th and 1/10th of a second. To assign this parallax is the same thing as saying that at the distance of nebulae the dimensions of the Earth's orbit would show a diameter which might range between 1/50th and 1/5th of a second, while that of Neptune would be more or less than 1 second. Great numbers of nebulae are, therefore, thousands of times the dimensions of the Earth's orbit, and probably most of them are thousands of times the dimensions of the whole solar system. That they should be completely transparent through such enormous dimensions shows their extreme tenuity. Were our solar system placed in the midst of one of them, it is probable that we should not be able to find any evidence of its existence. Considerably less conspicuous than the constellations, but composed of a far greater number of stars, are various clusters and systems which often contain several thousand individual members. It was the telescope of Galileo that first made possible the study of these clusters, for he saw in the Pleiades 36 stars where the ordinary eye could distinguish but 6. In other parts of the heavens, as in portions of the Milky Way, he could observe clustered together multitudes of fine stars, and in Praesepe, in the constellation of the Crab, he was able to count 40 stars. With additional telescopic power further clusters were noted, and Halley (1656 1742), for example, discovered a great star cluster in Hercules, which, now known as Meissner 13, later derived its name from the catalogue of the famous French astronomer and comet hunter Meissner (1730 1817). But it was Herschel, with his high powered telescope and his keen powers of observation, who was able to give the subject further research, and he became, as we have seen, greatly interested in the distinction between nebulae and star clusters. Herschel found that many of the nebulae recorded by Meissner could be resolved, and he immediately pushed observation in this field. The most recent theory of the formation of star clusters is due to Arrhenius, who states in Worlds in the Making that most of the clusters are found in the neighborhood of the Milky Way, where also the visible stars are unusually crowded and where almost every year some new star is discovered. It is in this region that collisions between stellar bodies are most likely to occur, and where gaseous nebulae would be produced. The nebulae, Arrhenius goes on to state, which are produced by collisions between two suns, are soon crossed by migrating celestial bodies, such as meteorites or comets, which there occur in large numbers. By the condensing action of these intruders they are then transformed into star clusters. In parts of the heavens where stars are relatively sparse, at a great distance from the Milky Way, most of the nebulae observed exhibit stellar spectra. They are nothing but star clusters so far removed from us that the separate stars can no longer be distinguished. That single stars and gaseous nebulae are so rarely perceived in these regions is no doubt due to their great distance. About 100 star clusters are known, and they comprise either groups of the brighter stars or densely packed gatherings where a large number of faint stars, as a rule between the 12th and 16th magnitudes, are collected. Of the first class the Pleiades are typical and perhaps the best known, though the Hyades and Coma Berenices, Praesepe in Cancer and Orion are also representatives of this form of cluster. The Pleiades contain 7 visible bright stars of about the 4th magnitude and cover nearly 3 square degrees, in addition to which there are a large number of fainter stars, some of which were first seen by Galileo. Of these 53 have been examined and their motions determined. Nearly 2,000 fainter stars are included in the cluster. They are less numerous here than in most parts of the sky, and even in the immediate neighborhood. The Pleiades, it must be remembered, are distant 267 light years, at which distance the Sun would appear to the Earth as a star of the 9th magnitude, and while these perhaps appear as a cluster, they are really something like 1/100th as far from each other as the group is from us, or 2 or 3 light years. In 1859 Wilhelm Tempel discovered a faint nebulosity near Merope, one of the brightest stars of the group, and on November 14, 1890, Barnard at the Lick Observatory noticed a second nebulous companion to this star and reached the opinion that the whole cluster contained a number of faint nebulosities. This opinion was confirmed by photographic observations, which showed that the entire group was embedded in a nebulous matrix which extended over a large section of the heavens and indicated that the stars, many of which, as brilliant as our own Sun, cannot be seen without high power telescopes, are intimately related in their origin and in their evolution. In Coma Berenices, containing 7 5th magnitude stars visible to the naked eye and lying east, south or west of the zenith on a spring or summer evening, there is an unusual grouping of lucid stars within a small area and in addition a large number of fainter stars. The cluster Praesepe in the constellation of Cancer, when seen by the naked eye, appears as a patch of nebulous light, but it is really a condensed group of stars, of which the brightest are of the 7th magnitude or just beyond the range of visibility. An interesting cluster is contained in Orion, where a circle 20 degrees in diameter, comprising the brightest stars in the constellation, was found by the late Professor Newcomb to contain 80 stars of magnitude 6.3. Of these 6 are of the 1st or 2nd magnitude, leaving 74 from the 3rd to the 6th. But this remarkable collection of bright stars has no unusual number of faint stars associated with it, and the conclusion reached is that the agglomeration of the brighter stars into clusters does not extend to the fainter stars where it is noticeable to the eye. Globular clusters containing a vast number of stars closely packed together are seen in the constellation of Hercules. It contains over 5,000 stars and is so bright that the naked eye can see it as a patch of light in the heavens, though the telescope of course can resolve it into a number of individual stars. In fact, 5,482 have been counted on a photograph taken at the Lick Observatory. Other clusters of this class are that of Omega Centauri in the southern heavens, which shows 5,000 more stars than the average star density of the region, and in the northern skies Canis Venatica and Pegasus. These globular clusters cover less space than the apparent diameter of the Moon, or less than 1/2 a degree, and the stars they contain vary from the 12th to the 16th magnitudes. Their composition is a disputed point. Whether the feeble appearance of the stars is due to great sums at immense distances, or whether there is a large number of small bodies among which the matter is faintly distributed. It is probable, however, that they are distant about 400 light years. The clusters themselves have vast dimensions and the stars of which they are composed are separated by great intervals. For example, in a cluster containing 5,000 stars, the average distance of one from the other might be 30,000 times the distance of the Earth from the Sun, so that they can move freely without danger of collision. The law of gravitation does not require any greater velocity for them than is possessed by the average star. A number of the individual members of these clusters are variable, but the reason for this variability has not yet been explained. The late Professor Newcomb says that perhaps the most important problem connected with clusters is the mutual gravitation of their component stars. Where thousands of stars are condensed into a space so small, what prevents them from all falling together into one confused mass? Are they really doing so, and will they ultimately form a single body? These are questions which can be satisfactorily answered only by centuries of observation. They must, therefore, be left to the astronomers of the future. Section 38.